Hi. In this lecture and in the next one, we're going to be talking about banking and payment security. This is a really important issue for the security engineer because an awful lot of the attacks that happen on systems are after the money. And we have to understand how things like online banking and credit cards and even cryptocurrencies work, because these are the mechanisms for fraud and the targets for fraudsters. So we already talked a little bit about bank security in the first couple of lectures. We looked at bulk compromise, how espionage agencies try and get hold of bank information at scale in order to do surveillance of target populations. There's also bulk compromise by crooks who, for example, may try and get lots of personal information from one bank, say from the Register of Anti-Money Laundering, information that people have given so they can use it to open accounts elsewhere. And there may be whistleblowers who are trying to tell journalists about bad things being done by famous people. Now, there are also more targeted attacks where a journalist might be after information about a celebrity, a rock star, politician, or whatever, and these are generally controlled by internal controls. In the old days, that meant limiting information on customers to the branches where their accounts were kept. And nowadays, it generally means delegated authentication, that the person in the call center can't see your account information until you've answered a few security questions. So the internal controls also work against insider fraud, against insiders helping themselves to your money and moving it from one account to another. But in this lecture and in the next one, we're going to be concerned mainly with how do you stop external fraud against payment systems. And our goal is to understand the world payment systems and through that to get a lens to understand cybercrime. Now here's a very rapid history of banking. If you go back to the 15th or 16th century, people used gold and silver coins, and the merchants would keep your assets in their vault for a fee. And then after a while, things evolved so that you just had a balance with them. You'd give the gold merchant your 20 guineas and he'd give you a receipt for the 20 guineas and you could go and get them back later. And then people added interest. You had deposits, loans, mortgages, various payment instruments that could be used to finance business and to finance trade. The next big innovation that came through was paper money, which was first seen by Marco Polo on a trip to China in the 13th century, and that gradually spread outwards from northern Italy. And by the time we get into the 19th century, we had a paper-based payment system with checks, bills of lading, all sorts of bits of paper that flowed around the world, and with them the money flowed too. So how did paper-based payments work? Well, some countries, including the UK, still use cheques, although other countries have abolished them. And a cheque is basically a written order to your bank saying, "Dear Royal Bank of Scotland, please pay Alice £100 from my account with you number 1234, signed Bob." So Bob makes out this cheque on a cheque form, posts it to Alice, she takes it to her bank, they pay it into her account. If her account is at the Clydesdale, for example, then the Clydesdale will send those cheques round to Royal Bank at the close of day and they will all settle up. Now, this was fine between mutually trusting parties, but the system was problematic because of scale and speed. From the user's point of view, it was slow. It took 3 to 10 days to clear a cheque, and during that time you had a note on your account that there was a balance of an extra £100 in your account, but it wasn't cleared yet, and so you might not be able to spend that money, or if you were, you could find yourself with an unpaid overdraft if the cheque bounced. Now, cheques sometimes did bounce, either because the drawer's account was out of funds, or when the cheque was presented to the drawer with their bank statement, they said, "Oi, this signature is forged." The whole process was very expensive for banks, and there were lots of different hacks in different countries to push back on fraud and make the system more workable. But by the time electronics came along, this was a system that was ripe for mechanization. So how do banks send money? Well, the simplest case and the earliest case that was tackled was the case of sending money overseas, because that was particularly slow, expensive, and unsure in the old days. And how things work is that banks in Scotland, for example, will have accounts at correspondent banks in other countries. So if you want to send your Aunt Agatha in Sydney in Australia $1,000, your bank will send to National Australia Bank, please pay Australian dollars 1,000 to AD Jones, account number XYZ, from our account with you number ABC. So this is a bit like a cheque, only it's drawn on an account that your bank in Scotland has at an account in Australia. So the technical question now is, how can you do this electronically? Well, from the mid-18th century, people invented the telegraph. Samuel Morse in America and Charles Wheatstone in Britain got telegraphs going domestically by various means. And then from the 1860s, we started to get international telegraph cables, thanks to Lord Kelvin, who pioneered the thing by laying a telegraph cable across the Atlantic. And the earliest users at scale among commercial firms were banks, because it enabled them to transfer money quickly and more cheaply and securely than with the old paper mechanisms. But the question then is, how do you stop fraud? Because in an old-fashioned Victorian telegraph, the messages went from one telegraph station to another, where they were copied by human operators. So what was to stop a human telegraph operator intercepting a message to the National Australia Bank and then making the payee one of his friends instead of your Aunt Agatha? Well, the answer was what was called a test key, which was basically a manual crypto hash. Now, here's a simple example, but it's not that much more simple than some of the weakest systems that people used. So what you would have is a table of random numbers with, and here we have the rows are by thousands of currency units, and the columns are by the mantissa there. So if you want to authenticate £376,000, you look at the thousands, and that's 6, so that's 71, and you write down 71. You look at the tens of thousands, this is the second row, that's 7, so that's 29, so you write that down. You look at the hundreds of thousands, and that's 3, so that's 54, so you write that down. And you look at the millions, and that's 0, so you write down 53, and you add them all up, and this gives you 208. And you then send that along with the message. Now, in practice, there were more numbers than this. The better systems tended to have 4-digit rather than 2-digit random numbers in the table, and the tables would be changed perhaps once a year in order to make it more difficult for a cryptanalyst to figure out enough of the values in the table in order to forge a telegram. The system is still cryptographically weak, but it kind of worked for quite a while. So what actually went wrong? Well, the most famous attack on telegraphic transfer was in the 1960s, the Security Pacific case, where a bad person at Security Pacific Bank in San Francisco sent a telegraphic transfer for $10 million to a Russian diamond company in Zurich. He'd arranged with them to buy $10 million worth of industrial diamonds. And he sent this on a Friday just before a Monday that was a bank holiday in America, but not in Switzerland, so that he'd have time to hopefully get away. And so he basically used an internal code that was used within the bank to authorize funds transfers from the telegram room. And the reason that this failed was that the internal procedures in the bank didn't support dual control. Anybody could go to the telegram room, and if they had the appropriate authority, which in this case was a password, then the telegraph clerks would make up a test key and send the instruction off. And the only way you had dual control, in fact, in the telegram room is that there were several people in the room where the code books were. And so one of them would compute the code and another of them would test it. But this didn't stop internal dishonesty. Now, although the cryptography was weak, there was only one attempted exploit that I know of in this period, where the dictator of an African country attempted to send a $10 million wire transfer to himself, and this failed because the whole country was in a $1 million overdraft limit. But nonetheless, people realized that it was weak and they set about producing a replacement. Getting the replacement actually up and running took something like 20 years, but the process started in the 1970s. The replacement for the telegraphic transfer system was put together in the 1970s by a consortium of banks who set up a jointly owned company called SWIFT, the Society for Worldwide International Financial Telecommunications. And this was basically an early secure email system that enabled any one member bank to talk to any other member bank. And how it basically worked like this: if you went into a branch of the Royal Bank of Scotland and send $1,000 to your Bank Agatha, to your Aunt Agatha, then the branch would send a message on its internal network to the RBS headquarters in Sighthill, where they would have the room with the machinery, which did SWIFT, and SWIFT had a set of cryptographic keys which had been exchanged with all the other banks with which RBS did business worldwide. So there would be a crypto key that had been exchanged with National Australia Bank in Sydney. And RBS would then send a message with a message authentication code on it to the SWIFT Regional General Processor in London, which would keep a log of the message that had gone through. The message would then be sent to SWIFT's headquarters with processing in both Belgium and the Netherlands, where it would be logged again. And it would then be sent to the Regional General Processor in Australia, which was down in Sydney, and that would then in turn send it to the National Australia Bank's headquarters, where the message authentication code would be checked. So here you've got separate measures for integrity, namely the message authentication code, and for non-repudiation, namely the logging. As for confidentiality, that was an issue because a number of countries at the time didn't allow people outside government to use cryptography, and so sometimes the local link had to go in the clear. Key management, that was done manually between senior bank managers, because when the guy from RBS went out to Australia to set up a relationship with NAB, he might take a key with him in an envelope and come back with a key from National Australia Bank in another envelope, or they could send it by post to each other's domestic addresses. SWIFT also supported dual control in that while Clerk A would enter transactions, Accountant B would check them and can change them, and then Manager C would verify and release a whole batch without being able to change any of them. And so you've got dual control between B and C, both of whom would have to collude in order to send a wicked message. Now, SWIFT at the time it was set up was owned by about 500 banks, and now it's owned by 11,000 banks worldwide, and it sends something like $125 trillion a year, which is substantially more than world GDP. But bear in mind when you hear such figures that it's the bank's own systems that actually balance the funds. And of course, funds are netted off at both ends, so banks just have to settle up from time to time if their bank accounts with each other get out of kilter. So how do you go about doing attacks on SWIFT? Well, some of the sophisticated attacks have involved sending guarantees rather than cash, because if you can persuade Bank A to give a guarantee to a customer of Bank B, then that customer can borrow some money against the guarantee and make off with it and be long gone by the time something is noticed. Whereas if you were to do an internal attack on Bank A and send money to Bank B, then the out of balance would be noticed within a day or two, and Bank A would be able to follow up and get the money back. The second thing that we learned with attacks on SWIFT is that if an attacker can figure out how to send money, the hard part is in the laundry step. There have been a number of cases where some programmer at Bank A put a message dishonestly into the SWIFT message queue and then turned up at a bank in Bahnhofstrasse in Zurich to collect the money and got promptly arrested because they didn't understand the difficulty of laundering money, and they didn't understand the context and the kind of controls that you can expect to have fired up if you suddenly turn up and try and take away $10 million in a carpet bag. Now, one of the most interesting large-scale SWIFT frauds that happened recently was in 2016, where the North Korean government stole $81 million from the Bank of Bangladesh. They tried to steal quite a bit more, and the full story is in my book. But the interesting thing here is that they managed to get away with some of it at all. And what they had done is arranged for their agents to set up in advance some crooked deals through a casino in the Philippines, so that when the money arrived there, there was a chain of agents ready to launder it through further organizations that would be resistant to law enforcement inquiries into money retrieval. Another aspect of attacks on SWIFT is attacks on confidentiality by law enforcement and intelligence agencies. Now, before 9/11, this tended to take the form of attacks on confidentiality on the local loop. But since 9/11, the American government basically demanded access to the entire SWIFT message stream, and after some humming and hawing in the European Parliament, this was granted. The Americans are particularly keen to track terrorist financing and to exclude Iran so that they can put on sanctions, and this has been one of the driving forces behind the undermining of financial confidentiality worldwide. Now, we'll come to that later when we start talking about anti-money laundering controls. The next component in the international financial payment system is the credit card. These started off in the 1950s in New York, where Diners Club and American Express introduced cards so that people could pay for restaurant meals and hotel stays, and they spread slowly as an elite product from one bank to another. In the UK, for example, Barclays introduced it as the Barclay card, and it was a status thing if you were a wealthy person to have a credit card. The other banks also introduced it and got in bed with MasterCard, which was the competing global franchise. This grew slowly because the difficulty in getting any payment mechanism going is that not many people want to have your credit card until there are lots of merchants who will accept it. And yet merchants don't want to go to the trouble of putting acceptance machines of various kinds in all the stores until enough of the prospective customers have got cards. So that took about a generation to get going, until suddenly in the mid-1980s, credit cards turned into a profitable mass market product. That's the time when you could use a credit card in just about any store in the high street. And by then, there was suddenly a race to add online authorization in the UK in order to cut the cost of credit cards, which previously had operated by imprinting a manual sales voucher, which the customer would sign a little bit like a check. And we also rushed to add PINs so that people could do cash withdrawals from ATMs. And of course, the banks were happy to charge transaction fees and interest as soon as you took cash out of your credit card. What also happened then is that once credit cards became a mass market product, we started seeing credit card forgery. And this was driven initially in the Far East, where people figured out that you could get credit card numbers and expiry dates from old sales vouchers or from carbon copies of vouchers that were discarded in rubbish bins, and you could then encode these on the magnetic strips of cards. And so we started adding card verification values to stop forgery. These are the 3-digit numbers that you see on the signature strip on the card, which aren't embossed and so don't end up being embossed onto a sales voucher, and the 3-digit code is different on the magnetic strip. So you can't generate a workable magnetic strip forgery of a card just from visual inspection of the surface. So that came later in the late 1980s. The third thread in the development of modern electronic payment systems was the ATM, the automatic teller machine. These appeared first in Britain in the late 1960s, and by the time I became a student in the early 1970s, how things worked is that we got punch cards. I had 4 punch cards, each worth £10 that I got every month with my bank statement. So I could take these to a cash machine, put them in, put in my PIN and get a £10 note out. And that was convenient because my living allowance for the whole week was £10. And so if I had needed anything more than that, I had to get my savings book and get money out the deposit account. Now, the early technology turned out to be a bit flaky because the banks hadn't done a particularly good job of encrypting the PIN code in the punch card, and once people figured out how that worked, they started forging punch cards and getting money out of cash machines. And so Lloyds Bank asked IBM for better cryptography, and IBM responded by supplying a cipher called Lucifer, a 128-bit block cipher that had been developed by a guy who had worked in identify friend or foe systems in the 1950s. The US National Institute of Standards and Technology then called for a data encryption standard, and there was a big political fight because the US National Security Agency demanded that the length of the key be cut to 48 bits, and eventually there was a long negotiation and it ended up being 56 bits long. This meant that by the 1990s, it was possible for people to break DES by exhaustive key search, and everybody figured that out back in the 1970s. But this gave the banks a cipher system that was good enough without it being good enough that it would tempt foreign governments to start using it instead of the stuff from Crypto AG that they were using, which the NSA knew how to defeat, as we discussed in the first lecture. So despite the fact that banking crypto started off with a slightly suspect block cipher, ATM Security really was the killer app. This is what brought cryptography into commerce, and especially ATM networking. This is something that I worked on for a few years in the 1980s. And the goal then was to link up all the world's ATMs so that if you were an RBS customer, you didn't have to go to an RBS to get money out of the cash machine. You could get out of Bank of Scotland too. You could go to England, get it out of Lloyds. You could go to America and get it out of Bank of America. So the idea was that your cash card would go with you wherever you wanted in the world and make your money available to you. So in order to do this, we needed an international standard which operated at a number of levels. And at the level of concrete security policy, the policy was that only the customer should ever know their PIN. There should never be anybody in a bank who knows any PIN other than their own personal PIN or who has the means to work it out. And how we implemented this was with a set of standard PIN transactions using cryptographic devices called hardware security modules, or HSMs, and these keep pins and keys from individual bank staff and enable everything to be managed under dual control. And then you have HSMs both at banks and also at the network switches at places like Visa, which translate pins as transactions flow from one account to another, and which also keep track of which bank owes which other bank how much money for their customers taking money out of cash machines. So let's have a look at how this works. If I've got an RBS card and I go to Barclays Bank ATM in London, I ask for £100 out and I put in my PIN. It's then encrypted at a hardware security module, a little potted chip which is glued into the keypad and is tamper resistant. And that is then sent to the acquiring bank, in this case Barclays, which has got an HSM at its headquarters up in Cheshire. And there the PIN is translated from the key that's used to encrypt it by the ATM to a key that's used in the ATM network, which could be Link in those days, or it could be Visa or MasterCard or Cirrus or whatever. And then at the ATM switch, it's decrypted from the key that Barclays used and re-encrypted using a key that Royal Bank uses, and then it flows through the network to RBS's headquarters in Sighthill, where they've got an HSM with the key that knows how to verify my PIN and can then send a message yes or no back through the network. Now, in theory, the response messages should also be authenticated using a message authentication code, but many banks optimized this step out, and as a result, we've occasionally seen attacks where some bad people manage to impersonate a whole bank. And sometimes you see a bank fraud that costs tens of millions of pounds over a weekend because somebody has managed to comes in. What else can go wrong? Well, let's look in the detail about how pins are generated. Now, this is the IBM system that IBM came up with in the early 1980s and made one of the international standards. You start off with your primary account number, or PAN, and in this, by international standards, the first 6 digits of the bank's identification number, so that tells you, 56 tells you, for example, that this is a MasterCard, and 4182 tells you which bank it is. And then you've got 9 digits of account number and 1 digit of a redundancy check, giving you 16 digits. So you then encrypt this number using the bank's PIN key, which is a 56-bit DES key, or nowadays a 1112-bit triple DES key, which gives you a hex string output. You then chop off the end. The standard says that you can have a PIN of 4 to 12 digits. Most banks standardize on 4 digits, 1 or 2 allow you to use 5. And you then decimalize the result. Most of the banks, all of the big banks in Britain except HSBC, decimalize by simply taking everything modulo 10, so B becomes 1 and D becomes 3 and so on. HSBC is different in that they've got a customized decimalization table. And so in this way, you've taken in a 16-digit primary account number and you've got out a 4-digit PIN. Now there's a similar process used to generate the CVVs, the 3-digit check values on card magnetic strips and on card signature strips, but these use different keys and they also use the card version number. That's beside the way for now. So one of the problems that people then came across is that some banks wanted to enable customers to change their PINs so that they could use more memorable PINs and hopefully use the card more and generate more transaction fees. So IBM came up with a system whereby you store an offset between the original derived PIN and your chosen PIN. So here, for example, is our bank customer. We've seen the primary account number, name is Mr. M.K. Bond, the balance is whatever, and the PIN offset starts as 0. Now, if Mr. Bond decides to change his PIN from 2213, that's the derived PIN that we saw in the previous slide, to 1979, say 1979 is his date of birth, then you simply encode in the bank record the difference, digit by digit, mod 10, between the chosen PIN and the derived PIN. And this means that Mr. Bond can use 1979 as a PIN, and the bank will verify the PIN as 2213 using its cryptography, and everything works just fine. But does it? So here's one of the early interesting technical attacks that came up in 1989. There was one bank that needed to issue everybody with new account numbers because they were replacing the core banking system with an incompatible one from a different vendor. And that was an enormous project that I worked on. It took years and cost hundreds of millions. And so what the bank did was to get the HSM vendor to add a new command to the API for the HSM to calculate the offset between a new generated PIN and the customer's chosen PIN. They did this incidentally after I'd left, so this wasn't something I had an opportunity to stop. And what then went wrong was quite interesting, because one of my successors pointed out that any customer PIN could now be revealed by calculating its offset from a known PIN. Because if I know how to calculate the offset between the natural PINs on two accounts, I can not only calculate the offset between my old account and my new account, I can calculate the offset between my account and your account, and so I can work out your PIN. Oops, said the bank, and they had to hurriedly contact the HSM vendor and get this new command taken out. Of course, the vendor hadn't figured out that this new command would break the world. And that was telling, because as time went on, banks asked for more and more transactions to be added to the hardware security module's transaction set, until by the early 2000s, leading models of HSM had as many as 500 different transactions to cope with different ways in which different banks worldwide did their cryptography. Then we started looking at it systematically. Mike Bond was in fact one of my research students who did his thesis clawing through HSM manuals and figuring out all the ways in which they could be broken. And this is one of the early ways that we discovered you could do that. When you set up the master key between two banks or between a bank and a cash machine, then what you do is you carry the master keys in 2 or 3 parts, giving them to separate couriers or posting them on different days so that you can maintain the dual control policy. If it's an ATM, for example, you might post one key to the branch accountant on Monday and then post the second key to the branch manager on Thursday. And that way you've got 2 separate people, each having one key component in their separate files. And what happened with the system that Visa had set up was that these components were combined using the exclusive OR function. And nobody realized it at the time back in the 80s when this was being designed, but this was a serious mistake. So let's investigate why. Suppose you've got a source HSM in a bank and a destination HSM, for example, in a cash machine. So the user, that is the program that manages the bank's ATM fleet, goes to the source HSM and says, generate a key component. And the HSM dutifully prints out on an attached printer in the security cage in the bank's data center the first key component. And it then returns to the calling process that key component encrypted under a master key. And you do that twice. And you then have 2 key components, which you can post out to the guy in the bank branch, and you've got 2 encrypted key components, KP1 and KP2. And to support this, the Visa cryptography had a transaction which would enable you to take KP1 and KP2, both encrypted under a relevant master key, and then get them back again, XORed together, encrypted under that master key. And keys of this type would then be treated as ATM master keys, and they could be used for tasks such as encrypting pins, or worse still, encrypting the pin master key so that you could do offline verification of customer pins. So what goes wrong? Well, the problem was this, that a single operator could feed in the same part twice. And since KP1 XOR KP1 is 0, this means that you get out the 0 key encrypted under a master key. And because it's encrypted under this master key, the HSM will treat it as being a suitably authorized key under which you can then encrypt a pin master key. And in this way, you could extract pins and you could extract pin master keys from a security module. So this was an attack, a slightly subtle attack, but once you've seen it, it's fairly obvious. And this had been in thousands of security modules sold by about a dozen different vendors to over 10,000 banks worldwide for a period of 20 years before the attack was observed. And that's one of the bizarre things about the design of cryptographic protocols, that they're just sufficiently subtle that you can have really devastating vulnerabilities in them which aren't at all obvious until, of course, someone spots them for the first time. And then you can have a long and expensive remediation process. And this and other vulnerabilities led to a process whereby pretty well all the world's security modules had to have significant upgrades or replacements during the early years of the 2000s. Many attacks were then found on hardware security modules because of the complexity of the pin management that they had been designed to support, without anybody, doing proper adversarial attacks on them at the time, back in the 1980s. Here, for example, is another attack where you use the existence of the decimalization table in order to work out pins in a slightly more indirect way than in the previous attack. So here's a typical pin verify command. You put in the primary account number. You put in a trial pin. This comes from somewhere, perhaps from an ATM, and it's encrypted under some key or another, but let's disregard that as a detail for now. And you put in an encrypted pin master key. That's the pin master key that was used to turn this primary account number into the pin 2213. And you then put in the decimalization table. And for all banks in Britain except HSBC, that was just the decimalization table 0123456789 ABCDEF, translated to 0123456789 012345. So what then happens inside the hardware security module is that it takes the primary account number, it takes the encrypted PMK, decrypts that under the appropriate master key, encrypts the PAN, gets the natural PIN of 2213, using the decimalization table, and then checks it against the trial PIN 0000, and are the two equal? No, they aren't, so it outputs no. So how can you adapt this? If you've got access to this transaction, how can you adapt this to work out pins? Well, the thing to notice is that the decimalization table is entered into the hardware security module unprotected. It's in the clear. And so what you can do is put in a malicious decimalization table, all zeros except for a 1 opposite the input value of 7. And what then happens is that when you encrypt the PAN, the raw pin's 22BD as before, you decimalize it, the natural pin is 0000, you verify 0000, and you now get a yes. And this yes tells you that there isn't a 7 in the natural pin. And I think you can see where this is going, and if you sit down and work it out, you'll reckon that with something like typically 22 or 23 transactions, you can work out what a customer's pin is. And the interesting thing about this decimalization table attack, which makes it still relevant today, is that first there's many different variants of it, and when we first came up with that, just about everybody that we told about it thought up a new variant, if they understood HSMs at all, because you can play with the decimalization table, you can play with the offset, you can play with pin block formats, you can play with all the variables in the system. But the general lesson from this is that this is a differential attack on a private computation. And nowadays, people are doing all sorts of fancy things with the cryptography on fully homomorphic encryption and private set intersection and so on and so forth, whereby you try and do some computations on encrypted data. Now, this is a very early example of how this got done in the 1980s, albeit using a hardware security module rather than fancy elliptic curve cryptography. And it went spectacularly wrong. And why? Because people didn't stop to think whether tweaking some untrusted inputs of a computation could result in private inputs being leaked. And this is something that people are still not checking properly today. And I predict that if we see fully homomorphic encryption being used at scale in real applications, we're going to see attacks that are somewhat reminiscent of this decimalization table attack on 1980s technology, which was so obscure that it was only discovered in the early 2000s. So there we have some of the interesting cryptographic stuff that went wrong with ATMs, which led to competition between HSM vendors and disputes over standardization and so on in the early 2000s. But this doesn't have very much to do with what actually went wrong in terms of fraud on the street. Now, during much of the 1980s, there wasn't that much ATM fraud. There were occasional incidents of it when people worked with corrupt bank insiders. And then in the early 1990s, we saw a growing tide of fraud, which happened because magnetic strip cards were easy to alter or to copy. And gangs learned to do shoulder surfing. Now, back in those days, the magnetic strip on your debit card didn't have a CVV, and so an early attack was to stand outside a bank and look over somebody's shoulder as they put their PIN in, as they did a transaction, and then if they dropped the ATM ticket on the ground, you'd pick it up, and in those days, several banks printed the full 16-digit number on the ticket. So you knew the primary account number and you'd observe the PIN with your eyeball, so you could then go and make a bank card and you could steal money from that poor guy that you just stood behind in the queue. And there were gangs learned to industrialize this. There were a couple of guys who got a furniture van and they put a video camera in it, and they had a motion sensor, and this would then observe people at the ATM and capture a videotape with timings on it, and they would then go and empty out the waste paper basket and pick out all the tickets with primary account numbers on them. They'd make up cards and they would loot the customers. That wasn't the only thing they did, but that was one of their tricks. And there was a big law case where something like 2,000 people sued 13 banks for £2 million back in phantom withdrawals. In addition to implementation bugs like putting 16 digits of the account number on the ticket, which banks stopped quickly enough, there were insider attacks. There was network diversion, where somebody pretended online to be a whole bank. We later on found malware in ATMs, and we had people social engineering pins for stolen cards. For example, if you managed to steal someone's purse and you found a couple of ATM cards in it, what you would do if you were a bad person would be to phone them up and say, hello, is that Agatha Jones? It's Barclays Bank here, Security Division. Tell me, we've seen a couple of transactions against your card with an off license in Newcastle for over £100 each time. These look like suspicious transactions. Did you actually do them? Oh no, said the customer, thank you for calling. My purse was stolen. I was just about to get round to calling you and tell you to cancel the cards. Okay, said the villain, that's fine, we've stopped that one. Now just tell us your PIN and I'll go into the computer and I'll stop your card for you. Right? And that worked often enough that it was a real issue and the banks had to go out of their way to educate people. What happened then from the mid to late 1990s is that fraud started to be industrialized using ATM skimmers. People invented devices that would sit over the throat of an ATM and would copy the magnetic strip as the card went in, and it then either had a little pinhole camera that would watch people entering their PIN at the keyboard, or else even you would have an overlay that sat on top of the PIN pad itself. And once people had figured out how to make these, they got various gangster associates around Europe who would actually act as their franchisees and would collect information from ATMs. And this led to growing problems with losses, and eventually the banks in the late 1990s decided to start moving to smart cards. So they started designing standards and preparing for a rollout of smart card-based systems, which started in 2004. They also developed a number of centralized intrusion detection systems which were capable of detecting fraud across ATM networks worldwide. One particularly neat invention by a New York firm called FICO signed up a number of banks who would report whenever they saw a dodgy transaction at one of their ATMs. And when that happened, FICO would put that ATM at the top of a hot ATM list. They kept a list of about the 40 baddest ATMs in the world at any one time. And the thinking there was that if somebody stole a bunch of debit and credit cards, they typically go to an ATM and try them out one after another to see if they worked. And so those banks that subscribed to FICO's service would pretty quickly find that their cards were not working in that ATM because it would rapidly go to the top of the hot ATM list. And therefore the subscriber banks found that the criminals were throwing their cards away on the street rather than actually using them to take money. So there are a number of clever ideas like that, but in total they weren't enough. And eventually, from 2004, the banks started rolling out the next generation of technology, the smart card. The cards that are used nowadays for payments, both for debit card and credit card payments, generally adhere to a standard called EMV for Europay, MasterCard and Visa, which developed this in the late 1990s and early 2000s. These were deployed from 2004 and unified to a certain extent the debit and credit card worlds. One of the ways in which this was rolled out was by means of what industry called a liability shift. The banks all changed their terms and conditions so that if there was a dispute, if a cardholder said, I didn't make that transaction, then if the merchant wasn't using EMV, it would be charged to the merchant. Otherwise, it would be charged to the cardholder because the bank would say, your card and PIN were used, therefore it must be your fault. You must be either negligent or complicit. And so the banks believed that it would pay for itself because they wouldn't have to pay for fraud anymore. The fraud costs would fall on the cardholder or on the merchant. So did things work out that way? Well, it changed a lot of things, but not always in the ways that banks expected. So let's think from the point of view of the economics of the security of PINs. Now, with checks, a fraud signature was null and void. And so if somebody gave you a check with a fraud signature on it, that was your risk. In other words, the forgery risk fell on the relying party. But with PINs, banks managed to arrange things in most countries that the risk would move to the user, and they got away with arguing to a complaining customer, your card and PIN were used, so you were negligent or complicit. So what could possibly go wrong? Well, this is the story of how fraud in the UK has evolved since EMV was initially introduced in 2004. And this is quite interesting, so we'll have a quick look at it now and then discuss some of the components of it in the remainder of this lecture and in the next lecture. The first thing that you notice is that card not present fraud, such as the use of credit cards online to buy stuff, absolutely shoots up. This is the first takeaway. It rises very rapidly for a few years until 2008, when it falls slightly, and then it starts climbing again, and it's still climbing today. The second is that counterfeit card fraud went down initially, but then it went up for several years because people figured out that once terminals were being used everywhere to collect customer PINs, not just ATMs, but also point-of-sale terminals in stores, it was dead easy to use false terminals to collect people's card and PIN data and then make up magstrip forgeries that you used in those ATMs that still accepted them. A number of the other types of fraud fell or stayed at a relatively low level, such as mail non-receipt and ID theft, which means impersonation. Mobile banking has started off since about 2015 and online banking since about 2010, and online banking started to climb from about 2013 or so, and we'll look at these trends as we go through. So as I just said, card not present shot up at once, and counterfeit took off once the crooks realized it's easier to steal card and PIN details once PINs are used everywhere. And you could use magstrip fallback for several years, particularly overseas. And what's also interesting is that tamper resistance didn't work properly. Now, in a later lecture, we'll discuss the mechanics of tamper resistance, but let's start off by looking at the security economics. Suppose you're running the merchant services division of a bank, and you can decide to pay an extra £10 per terminal to make 1 million PIN entry devices secure, and thereby save the UK banking system overall 100 million a year in fraud. Would you do that decision? Well, you would then say, well, what proportion of the bank cards are issued by my bank? And if your bank only issues 8% of all the cards in issue, then you're not going to bother doing that, because the bank spends £10 million and it saves £8 million, so that's not a business proposition. There are also issues within banks, because if the card division's manager, if you or the guy who goes and buys all these merchant terminals, and you're going to spend 10 million of your budget so that your rival, the card division manager, saves 8 million on his, then that's an even less attractive proposition. So there are significant issues of governance around here. And what we found for the first 10 years or so of chip and PIN being deployed is that PIN entry devices were trivial to tap. Devices were claimed to be evaluated under the common criteria, which we'll discuss later in the section on accreditation and evaluation. And it turned out that these were trivial to tap, and the evaluations hadn't complied with the requirements of the common criteria, and banks said no, it wasn't a problem, and the common criteria brand owner, GCHQ, just didn't want to know. And yet we found here, for example, with this Ingenico terminal was the most commonly used PIN entry device in the UK in the mid-2000s, we found it was trivial to tap, because in the back of it there was a place where you could put some wicked electronics, and if you drilled a hole where you can see that paperclip going in, that managed to drop a contact onto the serial line, which took the clear text pin from the pin pad to the card, and which got all the card data and transaction data coming back in the other direction. So with a wiretap like this, you could steal enough information to make a magnetic strip forgery of the card. Now, all of a sudden, there was concern in the industry because Shell found that it had to replace all its pin entry devices. These were actually of a different make from Trintech in Ireland. Bad people managed to figure out how to put bad electronics in them. And Trintech, in fact, went bust and retired from the pin entry device market. So eventually, the crooks taught the bankers a lesson in governance of such systems. And more lessons were to follow. Let's look in detail at a normal EMV transaction. You put your card in the pin entry device and the card says, "Hello, I'm card for bank account number so-and-so, and here's some encrypted stuff and a digital signature which proves that I am issued by such and such a bank." And the merchant then displays to the customer, "We'd like you to pay £59, please enter your PIN," and the customer enters 1234 or whatever it is. And the PIN entry device then sends to the smart card, the PIN is 1234, the amount is £59, blah, 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 various bits and pieces, and the card then scratches its head and says, well, okay, the PIN is right, and here is an authorization cryptogram. We'll look at the details later, but basically it is a cryptogram that's calculated using a cryptographic key that is shared between the card and the card issuer. So the merchant terminal doesn't know what that key is, so it can't verify it, so it sends the transaction with the cryptogram off to the issuer, which then checks the cryptogram and checks whether the customer has got enough money in their account, if it's above a certain floor limit, and then sends an authorization back to the merchant. And at a busy period, if the amount is below a certain threshold, then the transaction may be authorized offline without referring to the bank in order to minimize the volume of transactions it has to be dealt with. Now, in about 2010, some crooks in France discovered that there was a flaw in this system, and we started hearing reports of customers who had their cards stolen, and their cards had been used in transactions, and the bank said that your PIN must have been used, and the customers were insistent that it couldn't possibly have been. In one case, the customer had never used a PIN with that card. So what's going on? Well, we investigated, and we found that if you have got some means of interrupting the transaction, of intercepting the transaction, of doing a man-in-the-middle attack between the merchant terminal and the card, for example, using a fake card or using an overlay card, then what you can do is throw the PIN on the floor and tell the card that this is actually a chip and signature transaction instead, because these are allowed for some people and for cards for some countries, and the only difference is that a PIN isn't then sent. So the card then gets the transaction, thinking it's a chip and signature transaction, and then works out a cryptogram and sends it back to the bank. And this is the kind of device that is used nowadays to do a no-pin attack. This is an overlay SIM. You can buy these from Taiwan, and you can get a software development kit, and they're about 180 microns thick, and they've got smart card contacts on the top and at the bottom, and you can program them in Java Card so that you can manipulate transactions and you can use them to attack cards that you've stolen, or in other ways which we'll describe later. And what then happens is that the card thinks it's authenticated a chip and signature transaction, while the merchant terminal thinks that the customer entered the correct PIN. And if you then send the transaction with the cryptogram to the bank, at least 10 years ago, would happily authorize the transaction. Because determining the manipulation means you have to look carefully at the extra information returned by the card and by the terminal, and doing that across complex networks was a difficult thing to arrange. So how could the no-pin attack be blocked? Well, in theory, you could block it at the terminal or at the acquirer, at the issuer, but in practice, it usually has to be at the issuer because with terminal tampering, the incentives for the acquirer are rather poor. And although Barclays introduced a fix in July 2010, they removed it in December 2010, we think because of too many false positives. Other banks left their systems vulnerable to this, and some of them even asked for one of our master's student theses, which investigated this, to be taken down from the web instead. And we told them what they could do about that. But it wasn't until 2016 that British banks actually fixed this, and to this day we come across cases of British tourists in China who've had their cards stolen, where this kind of attack appears to have been carried out. And the real problem here is that the EMV spec is now far too complex. You've got 100 plus vendors, 20,000 banks, millions of merchants, and everyone passes the buck. And it's really, really difficult to change anything once a system has scaled up to that size. And what we've also found is that the API attacks we were talking about earlier on the HSMs keep on coming back. So for example, Visa defined a new HSM transaction to support EMV, where the idea was that you would be able to send a cryptographic key from one HSM to another as a text string followed by a key, and amazingly they allowed the text to be variable length. And this led to a simple attack where you could encrypt text followed by 00 and then text followed by 001 and so on, in order to work out what the first byte of the key was, and then by varying the length of the text you could get out the key one byte at a time. And this vulnerability turned up in all the compliant HSMs worldwide because Visa had specified it. And so basically what was happening is that as soon as the HSM industry removed API vulnerabilities, the banks put them back, because the governance of the whole system was basically shot. Now here's another example of how EMV went wrong, ATMs and random numbers. I said I'd look in detail about how the authentication request cryptogram is done, and here it is. The terminal sends a random number. This is known in the spec as the unpredictable number. We will just call it N here, to the card, along with the date D and the amount X, and one or two other things such as the currency code. And the ARQC is a MAC computed using a key that the card has and that the bank also knows on N, D, and X. So what happens if I can predict N for D? If I know what unpredictable number a given terminal will use tomorrow, and if I get access to your card, I can pre-compute an ARQC for that given amount and on that particular date. And how did we figure this out? Well, we got a complaint from a guy in Malta who had gone on holiday to Mallorca, and he ate a meal in a rather dodgy, perhaps mafia-owned restaurant, and the following day he found 4 ATM transactions on his account that he didn't make. And so he complained to HSBC in Malta, his bank, and they said, well, our system is secure and your card and PIN were used, so it's your fault and we're debiting you. So he demanded the logs of the disputed transactions, and he came to us, and this is what we found, looking at the logs, that the unpredictable number, which you can see in the right-hand column, ended up being a 17-bit constant followed by a 15-bit counter that cycled every 3 minutes. So we put together a test. One of my postdocs had some fun wiring up a bank card with a clock chip and a microcontroller and some memory, so we could take fine-grained timing measurements of bank transactions that we did around ATMs in the UK. And we found that a bit over 40% of ATMs in the UK are also simply using counters as unpredictable numbers. And the reason for this, we figured out, is that in the EMV spec, the testing for the unpredictable number simply says that the tester has to draw 3 numbers from the device and check that they're all different. Now, if you're a programmer in a hurry, then using a counter is a fast way of passing that test. So how does this work out in practice? Well, the Preplay attack that we found in practice around Europe was something that we first came across in 2014. A British sailor went into a bar in Las Ramblas in Barcelona, the big fancy street in downtown, and he paid $33 for 2 drinks, 33 euros for 2 drinks. And he woke up at 6 in the morning with a sore head because his drink had been spiked, and he then got on a plane to Paris, and he then checked his account, and he found that 33,000 euros had been taken from his account at Lloyd's in 10 payments of 3,300. So why does a sailor have 33,000 euros? Well, he was working out of Aberdeen on the rigs, that's why. And so he went to Lloyd's, and Lloyd said, your card and PIN were used, so it's your fault. And so he went to a law firm, and the law firm came to us, and we got the logs, and we found that 10 transactions had been made an hour apart for 3,300 euros each from the same terminal, but through 3 different banks and with different terminal characteristics. So this was clear evidence of technical tampering, and so Lloyd's basically grumbled a bit and gave him his money back. And the lesson here is that EMV lacks a trustworthy user interface. And so what a bad person can do is that they can monkey with the software in an EMV terminal and get it to display the wrong amount of money to you, so that you think you're authorizing a £30 transaction when you actually authorize £3,000, or that you're actually authorizing 10 transactions when you think you're actually authorizing 1. And this can also be done by sticking one of these overlays onto the customer's card before you stick it in your terminal. And we've seen a pattern of activity whereby these kind of scams are done in red light districts all the way around Europe. We've seen them in Poland, we've seen them in the Baltic states, and we have even seen them in the UK. In Bournemouth, the council had a dispute with a lap dancing club, the Spearmint Rhino, and the councillor came to us and they said that multiple customers had complained of excessive card charges. They'd go in and buy a drink for the young lady for 50 quid and they'd be charged 5,000. And sometimes they woke up with a sore head in the morning. And if they complained to the bank, the club just said, well, he was with 2 girls all night and that's what we charge. The banks and the police weren't interested. But the council was worried because, of course, if you've got an establishment that starts anaesthetising people while they've got full stomachs and without medical assistance, then sooner or later someone's going to end up dead and you've got a murder on your hands. And so the councillor got the Bournemouth Echo to speak to us, and they wrote about the Preplay Attack, and about 20 more victims contacted the councillor, and as a result the club's licence was restricted for 6 months. And still the police weren't interested. And we did what we could to try and contact the local authorities, but nope, that's not something that they wanted to do in Bournemouth, or also for that matter in Poland. And this is actually rather concerning. Now, when you think about it, the cards that you've got in your pocket have perhaps got a total overdraft ability of several £1,000s, quite apart from any money that you've got there. And the banks will very often give you extra unsolicited overdrafts so that they can charge you more money for them. So if you go into a red light district establishment with 3 or 4 bank cards in your wallet, it's as if you're going in there with £5,000 or £10,000 in cash. Now, would you go into such an establishment carrying 5,000 or 10,000 in actual banknotes? Well, hey, that's one of the downsides of card payment, that if things go wrong, they can go very wrong.